Hello guys, welcome back to my channel Gamma Digamma. Apologize for the big break in between, but it's just university, exams after exams, and life is stressful. But I think I owe this video. I mean, this video has been long overdue, and so has the video requested by a Russian guy whose name I keep forgetting. I don't want to mispronounce in the comment section. It was about Kumar's log gamma Fourier series. So good news for you, I figured out how to do it. I will make a video about the cosine integral function after this video, and then after that we'll be armed with all the tools we need to prove that log gamma Fourier series expansion. So stay tuned for that. Today I would like to just do an example of using the Wronskian to find the particular solution of a linear usually second order differential equation.
Hey guys, welcome to Gamma Digamma.
Okay, so this is basically the particular differential equation we have to solve. It's just the oscillator equation, the simple harmonic oscillator equation, because you have if you remove this driving function, you set t equal to 0, you'll have second derivative of y with respect to t is equal to negative omega squared times y. So how do we solve this? Well, what we do, if you remember the last video, is we found a way to find the particular solution given the two homogeneous solutions. My bad. So let's assume we don't know the homogeneous solutions. I mean, of course, there's homogeneous solutions, but let's just assume we don't know those solutions. So to solve that, let's first solve the homogeneous equation. So that's the homogeneous equation. Now I would like to use the method of quadrature that I've discussed in several videos ago, but I have made a video on that, so please check that out. Let me define the boundary conditions to use that method. Displacement at 0 is 1. Y dot, which is basically dy over dt, this y dot is this physicist notation, at 0 is 1. So the velocity, this is 0. The velocity is 0, displacement is 1. So you basically pull it initially and then the motion starts. If you use method of quadrature, you can write this as differential of dy over dt, entire thing squared, is equal to negative 2 omega squared y dy, and of course let's integrate both sides. So here we're going to integrate from dy over dt at time 0 to say time t. Here corresponding to that, we're going to integrate from y of 0 to some y of t. I hope this is legible. Okay, and when I simplify this guy will just become 0. So we have dy over dt squared equals negative omega squared, and this will be a y squared at t, so that's just this, minus y of 0 squared, which is 1 squared, which is just this. And of course take the square root on both sides, so we have dy over dt, which is y dot of t, negative omega squared, so if you take a square root, it's just omega, square root of y squared minus 1. Now we can try to plug in the boundary conditions because we don't know which branch to take. There's actually a plus and minus here. We don't know which branch to take. So let's just plug in both of them. If you plug t equals 0, you have y at t equals 0 squared, which is 1. 1 minus 1 is a 0. And this is also equal to 0 because y prime of 0 is equal to 0. So we have 0 regardless of like whichever branch we choose, like this equation will be satisfied irrespective of what branch we choose. So let's just, for the sake of some convention, let's just choose the positive branch. The negative branch has significance because it will generate the second solution, but I'm not going to generate the second solution based on this second branch. I'm going to use the Wronskian later on to generate that solution as well. So if we integrate now, this is separable. Differential equation is variable separable. We get, let's see, there should actually be an I here because if we take a square root, there's an additional I here. So I omega t integrated. This is at y at t equals 0, y at t, 0 and t. So this just transforms into, and if you want you can do like a trigonometric substitution, y equals secant theta so dy is secant theta tangent theta d theta. You can like do that substitution, forget the upper and lower bounds from it, we can resubstitute later. Secant theta tangent theta d theta over, you have an additional tangent, secant squared minus 1 square root as tangent integrated. This is just, I believe, should have been a dt here. It's I omega t. And this is secant theta, which is natural log of secant theta plus tangent theta, but we can resubstitute that back to get this expression. Evaluated it like y of 0, y of t is equal to I omega t. This is just natural log of y, square root of y squared minus 1, because y of 0 is like 1, so this is 0 and this is 1. Natural log of 1 is 0, so you minus 0, I omega t. Anti-log on both sides, so you have y plus square root of y squared minus 1 e to the I omega t. And now we have to get rid of the radical, so just isolate the radical and square both sides. E to the I omega t minus y, quantity squared, y squared minus 1, and we have e to the 2I omega t negative 2y e to the I omega t, y squared equals y squared minus 1, y squared drops out, and you just isolate the y because you have to solve for the y, and you get e to the I omega t. This is just basic algebra. E to the negative I omega t divided by 2. If you trust your complex analysis, this is cosine of omega t. This is why I call this y1. This is the first homogeneous solution. Now for the second homogeneous solution, and let me just change color. For the second homogeneous solution, we can just use the equation we derived in one of my videos. It's just this. Now this is actually the Wronskian here, but if you see the differential equation we started with, both of these guys, the coefficient for the first derivative term was 0 because there is no first derivative term. So if you remember the formula for the Wronskian, it was constant e to the negative that coefficient dx. Since that coefficient is 0, e to the 0 is 1, and the Wronskian is just a constant w naught. Or y1 squared dt. We know y1, that's just cosine omega t. Again, for finding this, you could have used the negative branch also from the previous relation. But let's just do this because we have the powerful tools now. Cosine squared omega t dt. Cosine squared in the denominator is just secant squared. Integrating secant squared is just easy because that's just a tangent omega t over omega. And don't forget the w naught. Tangent is sine of omega t over cosine omega t, so that cancels out and you have simply w naught over omega sine omega t, and that is the second homogeneous solution for the differential equation. So we have this, let me box them, and we have these solution, and we will use these now to generate the particular solution for this particular differential equation, which is not homogeneous because it has a driving term here. Okay, so let's do that now. Okay, so now when we get started, remember the formula. This is the differential equation. Remember the formula we derived last time, in the last video rather. Particular solution is given by y2 integral of y1 times the drive over the Wronskian, in this case dt, y1 y2 times the drive Wronskian dt. This was the linearly independent particular solution. Y2 is known to us, it's just w naught sine of omega t divided by omega. This is just cosine omega t, that's y1. Driving is t in this case, just the linear, over Wronskian will be w naught because it's a constant dt, minus cosine omega t over the omega from the sine inside. I'm just writing that out now. Sine of omega t within omega naught divided by omega naught times the driving function t dt. The omega naughts will cancel, so it doesn't matter what like Wronskian we had, it will just cancel, the constants will just cancel out. We have to do integration by parts here because it's a linear times a trigonometric function. So let's just do that. We can pull out an omega, so two of those, omega squared. Inside we now have a sine of omega t times t minus integral of sine omega t dt plus cosine omega t or omega square. I'm sucking in out a negative, which makes a positive here because of the sine integral there. Cosine omega t times t minus integral of cosine omega t dt. So this is certainly a big expression, but don't worry, it will simplify. That's probably why I chose such a simple drive. So now let's see what we have here. So we have t times sine squared omega t omega squared minus will be a plus, so omega t cosine omega t divided by omega cubed plus t times cosine squared omega t divided by omega squared minus cosine of omega t times the sine of omega t divided by omega cubed. And look, it's simplifying because this cross term goes away. Notice you have a t over omega squared sine squared of omega t plus cosine squared of omega t, which is just 1. So you just have t over omega squared. That is the particular solution for this particular differential equation. Okay, and you can try to plug this in. If you plug this in, the second derivative basically of this guy is 0 because t is linear. Omega squared will cancel, so you have just a t is equal to t, so it makes sense, it's satisfied. The most general solution is a linear combination of this particular solution and some like arbitrary linear combination of the homogeneous solutions. So say a times cosine of omega t plus b times sine of omega t. So the 1 over omega factor, I'm just sucking right into the coefficient b. And so this is the steady state solution. If you think of this as an oscillator, and this is the transient solution, because this will always be 0. You can plug this in, you'll always get 0 plus whatever this evaluates to the drive, right? Because this is the particular case. So y of p plus 0, which will still be y of p. So this still satisfies the equation. And we can like try plugging in some things we know. Initial conditions, y of 0 is like 1. So you do that. So 1 is equal to, this is 0, this is 0, a. So a is 1. We also know that y prime of 0 is 0. So 0 equals, this is 0 because it's a, or wait, no, it's 1 over omega squared, my bad. So it stays the same for all time. And then the sine, this will be a over omega negative sine omega t, b over omega cosine omega t. If you plug in like time 0, this will just go to 0, this will go to 1. So we have b over omega equal to negative 1 over omega squared. So b is just negative 1 over omega. So you plug all these things in, you get this. And there you go. That is the solution for this problem. This will work. And it's really, really nice. One thing I would like to point out is like, notice this case, like forget the Wronski and just notice cosine of omega t times the drive, sine of omega t times the drive. It actually reminds us of the Fourier series coefficient calculation that we used to do. And this makes sense because if you can express your drive function, this is your drive, in this case was a linear, if you can express your drive function as like a linear combination of sines and cosines, then this calculation just becomes so much easier because now you can just use orthogonality conditions, and like because the Wronskian is like a constant anyways, which cancels out. So all you have to do is just use like orthogonality conditions. And if you notice that if you like say choose some arbitrary frequency, I don't know, omega sub d driven frequency, you notice that this will become 0 and this will just become, this will just like sift out the driving frequency term from this, like pi times the driving frequency term. Again, we don't know the bounds of integration, but this should sort of seem like close to a motivation of expressing things in terms of sines and cosines, because then just makes our life so much easier. Because this integration, this was a linear now, but what if it's not? What if it's something else? And 2 videos later, I'm going to show you how functions like log gamma or like something else can just distort the integral to make it like a really, really hard problem. If you can express your drive function as a sine or cosine, then you can account for those like fundamental waveforms that the homogeneous solution guarantees us. It'll make more sense, it'll be more natural then. And you'll see the beauty of mathematics then. So stay tuned for that. I'm going to actually make a physics wave mechanics series, so I will definitely cover that then, and it'll feel more natural rather than forced here. Here the only forced is this force term, this driving term that's driving this. But that's it. I think that's it for this video. I hope you enjoyed. Please like and subscribe to my channel, guys. Recommend me to your friends. Spread the word of Gamma Diagram in the math community. Stay tuned for more content. There is more coming. I may not be so regular as I used to be several weeks ago, but I'm still alive. I'm going to still make videos because this channel is my life. It means a lot to me, and I'm sure it means a lot to you too. So thanks for watching. Stay tuned. Peace out.